So I looked at the I wrote some notes. So I looked at the PowerPoint and the homework a little bit, and it looks like, as I was just saying, there's two types of questions, and so as usual, I don't actually just want to like go in order of the homework. I'll just show you how to do the two questions. They're kind of not even two different questions, but it's just like even when you take a quantum mechanics class, like as an undergrad in physics, whatever, like even that, which is like a whole class for this, it's kind of like just this one problem. And there's different types of solutions. So it's just like the wave equations that we've been doing, but there's like there's just like once you know the solutions, you kind of can do a bunch of the homework questions without redoing this.
Yeah, because they're similar.
Yeah, exactly. And you probably at some point have to like actually show how you do the whole solution. I think like once at least on the homework, but once you show it, you don't have to like re-show it. You know the values and stuff. So, so what the thing is, well, okay. So in the PowerPoint, you talked about all the postulates of quantum mechanics, right? That was the whole. There's like 8 of them or something. So that's true, and those are all fine. But we don't really need to use very many of them. But the one we need to use is, and I wrote it down even though I'm supposed to know it. So this is the oops. I don't know why I wrote. Should be. This is the time-independent Schrodinger equation. Okay. So the Schrodinger equation is what literally that's one of the postulates, is that things evolve according to the Schrodinger equation. But and the reason they're called postulates, by the way, is because it's not really obvious what you're going to talk about when you talk about quantum mechanics, or when you talk about any field, really. Like like the idea that we talk about forces and objects, those are kind of postulates. We don't usually say it because they're like, sure, But in this case, we have to talk about this thing called the wave. So this psi is the wave function. And the postulate is that the wave function describes anything we care about in quantum mechanics. So all the questions that you'll find in this area will be about the wave function, or a particle described by a wave function. So that's the thing. So that's why we're solving a wave equation. So when they talk about particles and stuff, why are we solving this thing that we did with waves? Well, because last semester there were different things, but this semester in quantum mechanics they're described by a wave function. Particles are described. And another one is that if you take this squared, and of course you have to integrate over all space. So this will be like dx or whatever. This is a one-dimensional, by the way. I should put 1D, because of course you could have it in 3D if you put like the gradient or whatever here, but we're only going to do 1D. So this is the probability, say, from x
to x prime.
Well, sorry. Yeah. Okay. Yeah, x1 to x2 is the probability of particle, which is described by this wave function, between x1 and x2. Okay. So again, these are in the PowerPoint, but they're sort of in different places. So I'm trying to like compile them into like the important parts for these types of questions. And then the other thing is that, well, if the probability of the particle is between x1 and x2 is given by this, we kind of automatically get that, well, what if we do this? Right? If we do integrate over, and this is I'm integrating over x, and I'm integrating over all of space. Well, what if I wrote a wave function that, like, I don't know, x squared, right? Like, if psi was like x, and psi squared is like x squared, well, that, if you integrate it, is infinity. So that's not an allowed state. That just means that wave function is not, that's a function, but it's not a wave function. It's not allowed. So this has to be finite, and if we set it equal to 1, then that just means that's called this is called normalization. So normalization just means that any wave function we can like scale it. Like we can just say that psi we want to make it a times. Sorry, I'll use capital A times psi, and then when you plug it in here, you get a squared psi squared, right? Because we're squaring it, so a squared is here. And of course now we can just solve for a to get this to always be the case. We want any wave function when we take the probability for all of space to be 1. In other words, that means what's the probability of a particle between these 2 points? If the 2 points are plus or minus infinity, the probability has to be 1, because that means it's somewhere, right? If we get a thing where we can't do this, where it's like infinity and there's no a we can find that makes it true, then it's not, we did something wrong. It's not an allowed state. Does that make sense? These are like the conceptually.
Okay, so anything a times psi must
So,
equal 1.
Solve for a.
Okay.
The point, sorry, that's a good. The point of this expression is to solve for a.
Okay.
That's the point of this. This is not a definition. This is saying that because we can scale any wave function, we can always scale it. It's always still a wave function by a number. A is a number now. And if we can always scale it, well then we could scale it in such a way such that the probability of finding it over any place, the whole total probability has to be 1. Of course, that's sort of makes sense. Anything else wouldn't really make sense, right? If we had it more than 1, what's the probability is more than 1? Like it doesn't, it has to be 1 over all of space. Now it doesn't have to be 1 over some points. Like if you did 0 to infinity, maybe it's half, right? Maybe it's half probability both sides. Anyway, so the point of this is to solve for a, and this is called normalization. So normalization is using this equation to solve for a. That's right. So that's important too, because when they ask you a question on a quiz or homework or whatever, they might ask you to find the wave function and then normalize it, or find the normalized wave function. And you can't just write whatever you find for psi from the Schrodinger equation. You have to also do this step at the end. So anyway, and so the other, so this is like one postulate is this probability thing. Another one is that important one is that this E is a number. It's called the energy, right? And this is an operator. Operator means it's because it's like a derivative, right? An operator just means something that you put a function in and it does something to it. So it's kind of weird that on this side we have an operator, which is this number times this second derivative of psi equals a number times psi. That's sort of a weird, it seems like something doesn't match. Like it seems like the units or something don't work. So that's actually true that that's very weird. Okay, so in other words, so what that means is that this is not just like a standard wave equation. There's only certain solutions we have, and they're called, I'll call them eigenstates. Did he say this in class? And then the number E is called the eigenvalue. So the eigenstates are the psi, such that this is true. Eigenvalue is the E. These are really called eigenvectors to another, but anyway. And what we want is to find when these are true, because the wave function, again, like we've said with all this, the wave function is not just a function that you could write any function, right? It's only certain ones that satisfy these certain properties. So let's do the actual example, because I've been talking abstractly for a while and it sort of could seem to not make sense for a minute. So I'm going to erase this, and we're going to do the infinite square well. So this is the standard example. So infinite square well. So sorry.
Is that the same thing as like the infinite quantum well?
Yes, yes, it is. So I actually left out, it's supposed to be like plus v. Sorry, it's supposed to be like plus, I don't want to do this, maybe minus v. I'll put a minus v here. Sorry. So v is the potential function. Okay, now if you look up in the book, the v might be on the other side, it might be whatever. Those are all just annoying little convention things. The point of this equation is that this is actually like a kinetic energy. The potential energy is like this part, and on the other side you get just like the energy left over kind of thing. So this is the time, and time independent because I have no t anywhere. In the full Schrodinger equation there's a t, There's a derivative with respect to time on one side, but we don't care about that. So the infinite square well, when they tell you, so here's I'll say, this is a quantum mechanics problem. Okay, it's called this, and what it means to give you a quantum mechanics problem and to ask you for the wave function, the solution, and the energies, is they give you, I meant to write it up here. Quantum mechanics problem is given a potential of x, a function of x, we want psi and e. This is most quantum mechanics problems we're given a potential over all of the space. Now, in this case, we're all doing one-dimensional problems. And we want the wave function solutions and the energies of them, okay? Now, infinite square well is a sort of shorthand for a specific v, and it's this. It's a piecewise function. You don't,
Oh God.
piecewise, yeah. A piecewise just means that it's not, you can't write a single, exactly, right. So in this case, and they're all going to be piecewise, by the way. Anything with the word square in it is going to be piecewise because you can't write like sine or something to make a square. You have to literally make it. So what it means is that the potential is infinity at x is less than 0. The potential is 0 at x. I'm sorry. I'm just making this up. Less than x is less than a. Say less than or equal to, and then infinity again at x is greater than a. Okay, so they might write this. Now, of course, this is just another way to draw. If we draw it, and this is the potential v, and this is 0, and this is a, that just means that over here, the potential is like infinite. It's, really, really high. And also past a, greater than a, like that, right? But between here, the potential is 0, okay? Now, potential being 0 just means it's like a free particle. But of course, if the potential is infinite, there's literally it doesn't have enough energy to get through. It's like it was a hill, but the hill is infinitely high. So there's literally no way you're getting anywhere through. You're not going to tunnel through this. You can't do any of that. Yeah, okay. And so now this is the problem. So we're given v, now we want to find the wave function and the energies, right, of the states, the eigenstates they're called, and eigenvalues. So what do? Well, we solve the Schrodinger equation. We know that the wave function satisfies the Schrodinger equation everywhere. Now, if we go to a point less than a, so there's 3 regions. Sometimes they'll write them as 1, 2, and 3. This is also a very common thing to label them with Roman numerals, the regions, because we know, because they gave it to us as a piecewise function, we might as well write the 3 regions like this. So in region 1, what do we have? Well, the potential v here is infinite, and so we're going to see that it's not going to be well defined. Like there's no function whose second derivative is infinity times the function itself. The function is going to have to be 0, is the moral of the story. And we kind of know that intuitively because if the potential, again, is like the height of it's like potential energy, right? It's like the height of a wall. The probability of finding the function, the particle there is 0 because it cannot possibly get anywhere inside the wall. There's too much energy it needs, right? So in region 2, so let's do region 2 first. We'll just do region 2 because that's all we can really do. Now we plug in the Schrodinger equation, so we just write this again, 2m d squared psi dx squared equals e minus v of x times psi. Okay, and now we plug in, because we're in region 2, v is 0 here, right? So because v is 0, we can just erase it, and we just get e psi. Okay. Great, and now what do we do? Well, let's try to solve this. It'd probably be easier if we get the derivative completely by itself. So we can rewrite this as minus 2me over h bar squared. Let us rearrange this. Psi equals d squared psi dx squared. So I'll segment. I just switched a bunch of stuff, but it's the same thing, right? All right, now this is a type of, this we've seen before. It might look a little weird now, but we've done this exact equation before. This is an equation where we want a function the solution is a function whose second derivative is proportional to the negative version of that function itself. Remember that? Well, anyway, we did I'm trying to remember, the harmonic oscillator, that's what it's called. The spring, right? Because remember the spring had this is the like
So it's
MA.
like the K.
Exactly, so this is the K. Now we don't have to, that would be hard if we had to remember all the, we don't have to remember, we can just say that, well, we know that that psi is going to be, the solution is going to be A sine kx plus B cosine kx. The reason we know it's this and not the other one we could have gotten is like e to the I kx plus e to the minus I kx. Remember, this is like the complex one. Or sorry, these are the same thing. I'm sorry. These are the same thing. We could have gotten e to the kx plus e to the minus kx. But this one, if we take two derivatives, we'll see that it's actually going to be the positive, like for whatever k is. It's not quite going to, well, I guess we could set k to be that thing. I mean, I guess it's just sort of whatever you want to, yeah. We'll get to this in a second, because we're going to use this when we do the tunneling. This is going to come up. So you could use either of these actually, because they both solve the equation. But so anyway, this is the solution, right? But again, like all the problems with the oscillating spring stuff, we have to plug this in to here to see the answer. And we know that this is another postulate of quantum mechanics, is that the wave function and its, I should write this somewhere. Let me write it here. Psi and d psi dx must be continuous everywhere. So this is like a rule. If these aren't true, then it's not a proper wave function. You can think of maybe the reason why is because then we couldn't do this integral and find the probability everywhere and normalize it. So there's all sorts of ways we could write functions that could not be wave functions. So these are all the requirements that go from the whole space of all possible functions that we could write to the space of possible wave functions, which are living in a space called Hilbert space. I'm not going to go into it, but that's the mathematical definition of it. Anyway, so these must be continuous everywhere. Now we know that the wave function at 0 must be equal to 0. And the wave function at A must be 0 too, because we knew that outside here, because there's infinite potential, the wave function must be 0. Right? So we know, therefore, that if psi, the wave function, is continuous, it can't just jump here. It has to be 0 at the endpoints. So therefore, if we use, running out of space, if we use, hold on, I'll erase this for now. If we use psi of 0 equals 0, which equals psi of A. So we already know this. This isn't from anything here. We know this from these parts and the fact that this is continuous. Then this will tell us that if we plug in our test solution, which is this, we'll see that that cosine, well, I mean, you know that at 0, if we plug in x equals 0, cosine is going to be 1. And then we're never going to get 0, so b has to go away. So this is the same type of problem we did last semester. And so we get something like A sine k. Okay, so if we plug in 0, this doesn't affect this condition, but if we plug in A, this is A sine k times A now, because I plugged in A has to be 0, right? And now what do we get from this? Well, we can cancel, divide by big A. I'm sorry that I'm using big A and little a, but that's actually what they use usually, so that's why I want to do it. And therefore we get Ka equals 0. So what must Ka be equal to? Well, this is like n pi again, right? Remember that's the what we had before.
Where is that impact?
So sine Ka equals 0. So when does sine 0?
Oh, when.
It's when the argument, whatever's in here, must be
Yeah.
n pi. Yeah. Now, actually, there's a little bit of it's a little bit different than last time because if we, for example, when n is 0, last semester when we did these problems, n could be 0 and that's fine. We would just get sine of that gives you that k is 0, and then you get like the flat 0 function, and that was totally fine last semester because that solves the differential equation. But in this case, if we want it to be normalizable, there's not enough space, but we needed the integral over all of space to be 1, right? Times a constant. But if the function's 0 everywhere, we're never going to get the integral over all of space to be 1, right? If you take the 0 function, the function that's literally equals 0 everywhere, you can't possibly multiply by anything to get it to be equal to 1. So that's a non-normalizable state. So that state is actually not allowed. So n cannot actually be 0 in this solution. That's not a solution. It's not a quantum state. It's a solution to the differential equation, but it's not a wave function anymore. And remember, when it's negative, well, that gives us the negative wave function, so that's fine. You know, you could just, it doesn't really matter about the negative sign. You're going to get the same function itself, but you can count them twice if you want. Okay, so now we can solve for k. That's the thing we don't know. A is a fixed value given by the problem, right? The problem literally gives you a. So that's a constant. N we just got is, we said it can be any number. Pi is obviously constant. So we could solve for k is n pi over a. And now, great, so now we have a sorry, okay, I realized I forgot a thing. There's an unless. I know, it's really annoying that there's an unless, but there is an unless v is infinity. I know that sounds like I just made that up, but that's a serious thing I totally forgot about. Unless v is infinity, then d psi dx is not continuous. There's probably a better way to say that if I erased it and wrote something else. But so what it says is that psi is always continuous. The wave function is always continuous. Otherwise, it doesn't make sense to talk about it as a wave function representing a particle. If there's a big jump, that what does that mean? So the particle, like, it doesn't make sense. So, but d psi dx, the derivative, also must be continuous, but not if there's an infinite jump in the potential. And here there is an infinite jump right here and right here. So we don't actually require, and you can kind of see why I thought of this now is because sine, of course, is going to look like this, right? So it's the harmonics of like a string on the space. This is the same problem as that. But of course, you can't possibly make the derivative be, like, you can't make it be flat at the ends too. So this would be impossible if that was the case. But there is you don't need it to the derivative to be continuous if there's an infinite jump in the potential. And there will pretty much always be until we get to the quantum harmonic oscillator, which we'll do
Oh my god.
in a couple, probably in a couple weeks, maybe next week, which is even more fun.
I'm sure it is.
Okay, so now we have this. So now we have a solution, and I'm running out of room. So I'm going to, I kind of want to keep this. Okay, I'm going to erase this line, which is just the Schrodinger equation, and write our solution is a, psi is a. Now we're going to leave a, because remember, later we're going to have to normalize it. So we have to leave the constant up front. Sine n pi x over a, and that's it. There's no cosine, remember, because remember cosine would give you an amount at 0, like a positive amount of 0, and it wouldn't make psi continuous anymore because psi is 0 here. So So that's fine. Now, actually, so we're good for this. This is an index now n because there's different solutions. It's not just one. With all of these, there's usually many solutions. So we actually have psi. We have psi. It just depends on n, and that's it. And this is gonna, if we graph it, it's gonna look like, well, if n is 1, we'll get this, right? If n is 2, we'll get like this. If n is 3, we'll get 3 things. Now it looks weird that it's going underneath. But remember, this is just the wave function. This is not like the probability where we'd have to square it. So when we take the probability of actually finding a particle, we're squaring it, and every time we square it, of course, we get something positive. If you square any number, you get something positive, right? Any real number. And if we square it, everything's gonna be positive, and so of course the probabilities are always gonna be positive. So don't be worried that there's negative numbers in here, that the wave function is actually negative valued in some places. That's fine. Because the wave function we can't measure directly, we can only measure the probability, which is the square of the wave function, the integral of the square of the wave. And now the other thing we needed to find, remember, was the energies. That's the only other thing you need to find. Well, how do we find the energies? Well, we still have the Schrodinger equation. What if we just plug back in and see what happens? Well, if we take 2 derivatives of psi, right? So we're going to plug into right here. So we get psi is going to be, so we have 2 derivatives of psi, we're going to get a, and now 2 derivatives is going to be n squared pi squared over a squared, right? And then 2 derivatives is going to be minus sine of n pi x over a, right? Does everyone follow that? I just took 2 derivatives of this. So I got 2 copies of everything inside, and I went to cosine, then I went to minus sine. So I get the minus sign here, and the a is right here. And on this side, I get minus 2me over h bar squared times psi, which is a sine n pi x over a. Now, because here's the thing. Remember I said before, it matters that we're in an eigenstate. An eigenstate means that we have something over here as a copy. Like this is a number times the function equals this operator times the function. That's not always true. That seems a weird thing to do. But because we're in an eigenstate, that literally means that you see how we have a sine blah, 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 a sine blah, blah, blah. It's the same exact thing, so we can cancel them. So this is the reason it's really important. If we couldn't cancel it, we'd get some x dependence, and that would be nonsense. So now we have literally a relation. Now it looks really messy. I'm sorry. If you write it, hopefully when you write it, it looks much nicer. But we have minus, also the minuses cancel. That'll come back later, trust me. So the minuses cancel, we get 2me over h bar squared equals n squared pi squared over a squared. Got it? Now, remember, what are we even doing this for? The reason we're doing this is to find the energy. Energy's right here. So all we need to do is solve for the energy. So we get n squared pi squared h bar squared over, this is an n, yeah, over 2m a squared. And this is now e sub n. This is an index because it depends on n. And that's it. And so these right here, this is literally, that's it. The whole point was to go from the potential they're giving us, which is called the infinite square law, which is equivalent to this, to get the states and energies. And that's the whole thing. And remember, you kind of also should write n is greater than or equal to 1 here, because n can't be 0. And you can forget about, again, like I said before, don't worry about the negative. Of course, n can be negative and it still solves everything we needed. But for a negative n, sign of a negative number is just negative sign of the number, and it doesn't really affect the wave function very much. Like, it just negates this. And again, everything we care about happens when we take the probability, when we square it. And when you square it with a negative number, it doesn't matter. So, or you don't have to worry about that every time. You just have to know that. Make sure not to. I don't know if you'll get points off. Probably not. I mean, not on homework. I don't really care. But you probably, unless they specifically ask, you should not write something that implies that it can be 0. Actually, here's a good example. On homework, probably on like 3 of them or whatever, it literally asks for the ground state. So what is the ground state? That means the lowest energy state with the lowest. So what's the lowest energy state? Well, if you said it was 0 and you put E equals 0, that's wrong. That is not a valid state of this because it has a wave function. So the reason is if you plug in 0, it works out. It just gives you E equals 0. So what's wrong with it? It solves the Schrodinger equation, right? That's true. It's all true. But it violates the fact that if you plug in 0 here, you get the wave function is flat 0 and it's not a normalizable state. You cannot make the integral over psi squared dx equal to 1. This has to be true. Of course, if you have the wave function be 0 everywhere, the integral over all space will be 0, and there's nothing you can multiply it by to make it 1. Yes.
What's like the physical meaning of this? Like, how does this apply to electrons?
So electrons obey. So electrons are particles, okay, but they're not like little like you might think of them as little balls bouncing around, but of course they're not. That's the whole point of the quantum mechanics is that they don't. There's all these like the double slit experiments of all points to those are things that the last semester you talked about that give you some ideas of what they were thinking of. You can't look at the double slit experiment and figure this out. Those are just ideas of why the standard explanation is wrong. They don't behave like if you took a bunch of like tennis balls and like shot them through things. It behaves very differently. So it's not just like a very small version. They interfere in such a way that they actually are described by waves. But then we might think, well, in some sense they are particles. Like you can't have half of them. Like a wave, you can have half of a wave, and waves can there's things waves can do that particles don't usually do. So what the explanation is that when you pick here, if you have a particle in this potential, so a particle can be in a wave function can be in this square well. If you say I'm going to look between here and here, I'm going to send a probe and see if I can see my particle in this half, right? And if it's in let's say the ground state. So I know my wave function, and I guess I know my energy, it doesn't really matter here, but if I know my wave function, if you wanted to find the probability to find your particle between, like an electron, between A over 2 and A, which is this half, right? What you would do, how to answer this question. Now, if it was a classical mechanics question, you would have to solve some kinematic equations and be like, the ball has a velocity this and that, right? But we can't use any of that because there's no such things as velocities or anything like that here. All there is this wave function, and the answer to this question is the probability is equal to the integral between A over 2 and A of psi, whatever your wave function is, squared dx. That's literally the answer.
Okay.
If you now the other thing you might ask is in classical mechanics you might say why can't I just say when is the electron right in the middle, right? But in this case, the wave is never right in the middle. You know what I mean? The wave is everywhere. So it actually that's one of the harder. There's many things in here that are very difficult, obviously, and there are many things in here that I don't want you to have too much difficulty with because I think it's just a renaming of things we've done last semester. Do you know what I mean? So the solving the differential equation, I don't want you to have too much trouble with that. If you're having a lot of trouble with that, you might be overthinking it, is what I'm saying. But there are other things that are actually new and difficult. and I mean, they were difficult last time, but I just mean, I want to make sure you're focused on the right new things and not just getting hung up on solving a differential equation where the solution's always like this. Great. And so actually, let's just do it. Let's just say the particle is in the ground state. So the question might be ground state of infinite square well. A particle. So the question would be something like a particle is in the ground state of an infinite square well with width A, right? What is the probability that you find it in the right half? Okay. Now you can kind of think by symmetry, it's probably half because it's half and it sort of looks evenly distributed. But let's just make sure. What do we have to do? We have to take this wave function, square it, and take the integral. Where is this? And now, well, the ground state is what? Well, remember, this is not, these are not wave functions, but these are sets of wave functions because there's an index n, right? The ground state is the lowest value. It's actually the value for the lowest energy, specifically, that's more precise. So when is the energy the lowest, as we just talked about? 0 is not a valid state. So it would have the lowest energy, of course, but it is not a valid state because it is not renormalizable. Sorry, it is not normalizable. Renormalizable is the whole other thing that you won't learn about, don't worry about. But it is not normalizable. But n equals 1 just gives you just this one, and that is normalizable. It does have a value. We could, I don't know what it is. Actually, sorry, we do have to normalize it. I forgot about that. We have to find a. It's just another variable we have to find, right? We didn't find them all yet. So this is our normalization condition. So let's take the ground state. The ground state, remember, is n equals 1. And let's do this. So when we square it, we get, well, a squared, of course, sine squared of pi x over a. Right? And this has to equal 1. Has to equal 1 is a condition now because we're going to solve for a. And so, of course, a squared is, and now, I don't know what this is. It's like radical, it's like 2 over a or something. I don't know. Do you want someone want to look this up? The integral of.
Is it like
Let me.
on the internet or like in the
It's
book?
probably in the book somewhere, but I don't know where. I could do an interval from alpha real quick.
Off
I
the top
think
of
it's.
my head?
I think it's 2 over a, but I'm not positive. Squared. Oh, sorry. And the integral is, remember I said it's negative infinity to infinity? But remember that the wave function is 0 outside of these bounds.
Yeah.
So we don't really, like, the integral, of course, of the wave function, if it's 0, the integral is going to be 0 too. So we can actually do the integral from 0 to a. Actually, oh. A squared, a, okay, so it's a over 2, apparently. Oh, sorry. A squared times a over 2. Okay. Not sure why that bothers me. That's fine. Okay, and this equals 1, and so therefore a itself equals radical 2 over a. So there we go. So it's just a number. This is like a standard thing, like in a, it's probably in the book I don't want to look through it now, but in the book somewhere they'll do it and they'll literally show you what this integral is. There's probably an easy way to do it that I don't remember, but anyway. So, okay, so our actual wave function is, our ground state wave function is radical 2 over a sine pi x over a. Remember, again, this is the ground state. Okay, and we have to, of course, square this and then integrate it from a over 2 to a. And when we square it, we get something that looks very similar, actually. But we don't get 1. Again, you'd think, isn't this kind of what we just did? But of course, no, because then we integrated 0 to a. So it's the same, it's the same integral, but it's, so it's going to be 2 over a, no room anywhere. So it's going to be like 2 over a times integral from a over 2 to a of sine squared pi x over a times dx. Okay, anyway, and then you do it and you get a number. And you should literally get equal to 1/2. It won't be some weird thing where you have to read off one. It's literally equal to the probability. And it should be 1/2. If you want a textbook that's good,
So
Then-
where are you gonna go with that?
I mean, so I don't know. I didn't actually read because I don't have a copy.
Well, if you're at the PowerPoint, you're at the book. Yeah.
Oh, is that what literally what's?
It's word for word.
Oh, okay. I mean, see if he does this exact problem, like exact problem meaning he does the integral.
Mhm.
I just feel like it's kind of literally how I do all of these is I remember when I took the class, I just memorized what all these were. I'm sure there's a way, there's like a trig way that's like, oh, you carry the 2 over like there's some little stupid thing that you can remember how to do. I don't know what it is. It's not very interesting. So at some point, just try to see how you do these squared trig integrals because they come up a lot here because of course the wave functions tend to be things like sine, and to find probabilities you're going to have to square them. To normalize them, you're always going to have to square them.
Is this it?
That might be.
That's how I look like I know.
Yeah, that's very similar. Oh, but they're using the complex form. I mean, it's the same thing. Okay. I just thought there was like a one-dimensional infinite well. Yeah, okay, so they do it the same way, but they use the complex form. I guess it's nice to see that way. This should be the same. Yeah, I think it is. Yeah, so if you're following along in the book, it's equation 9.33 is literally what we just did right here. They talk about, here we go. Yeah, so equation 9.35 is where they actually literally do this integral. So they don't really explain it either. Anyway, whatever.
Classic.
So, and then they write 9.36 is literally where they write the solutions they fill in the A. So I'm just saying, so yeah, okay, that's good. Great, and it says infinite square waves or standing waves, sure. Do not have any average momentum. Okay, so then in 9.38, they ask you to find the momentum, the average momentum, and to find the things like the momentum. So remember, this was trying to find the position. To find something like the momentum, we would have to use, this is the average momentum. This is is in the PowerPoint. It's like one of the postulates of quantum mechanics. We'd have to use the integral of, and it's going to be psi. So remember, psi squared is actually like psi star psi. It's like the complex conjugate times itself. Now in this case, we're doing everything in real, so we don't care about that much. But in the book, they do it in the like e to the I kx. So-
In place of what?
In place of this. So we
Okay.
use the real version. Remember,
Okay,
could also
okay,
write-
so it goes back to the A and B. Or like
yes, yeah,
A and
you could also do this entire problem with, instead of this as your solution, you could do e to the I kx plus b e to the minus I kx. And remember, by Euler's formula, they're going to be the same. But anyway, which I guess maybe they want you to do, but whatever. You could do this, but then you put in the middle, so instead of this, in the middle you put the momentum operator, which they tell you what it is. It's like this. Something with h bar, there's like an I or something, whatever, and you get dx. It's not squared or anything, but. And so all you do is just, so I think, is that what it says? Sorry, I just wanted to. Minus I h bar, okay, sorry, I forgot a minus sign. So it's minus I h bar. So all you do then is just take your wave function, which is psi, take the x derivative of it. These are just numbers, I and h bar is just numbers, multiply by this, and then do the integral over the whole thing. If they ask you for the average momentum over the whole region, then you just do 0 to A. I don't think there's any homework questions that ask you about average momentum.
No.
Okay, good, because it's a little annoying. It's the same. It's just, remember, this is one of the things where they say if they ask you to find, this is called the expectation value. It just means the average. The expectation value of an operator, a quantum operator, then you just sandwich it between the wave function and this integral, and take the integral over the region you care about, that you want to measure it on. Now, if we did it, And in the book, they explain the answer. And I would just say if you want to see this in the book on just page, sorry, I just want to see what page it is. 163 at the top. This is where they sort of derive it. And so yeah, they just show how you do it, and then they say that the answer comes out to be 0, and that makes sense because what is the average momentum of a state in this box? Well, if it wasn't 0, like where's it going? Like it's better be 0 because it can't go anywhere. It's not like a standing wave, or sorry, not a standing wave, a traveling, like a free particle. Free particle can have a momentum. It could just be going left or right or whatever. Nothing can go between here. It's like, you can have standing waves are made of things going left and right, but they always cancel because it's not going anywhere. So anyway. Okay, so now, is everyone okay with this? So the main point of this is that we can get these two solutions. This first thing is almost identical to the guitar string type problem, right? Where we find the wave functions of the guitar string. I'll even write that. But the difference, though, so the mechanism is the same. The differences that you should be thinking about, though, is that on a guitar string, they just tell us that the ends of the string are fixed, and we just believe them, which is fair enough. We should believe them. In this case, they don't. There's no fixed strings or anything, but we know that the potential at the sort of what would be the ends of the string is infinite, and therefore we know the wave function must be 0 there, right? Because it has no, the wave function has some energy E, but compared to the infinite amount of energy, it's nothing. It has to have 0 energy. So the wave function literally has to be 0 here, and the reason why we know that makes the endpoint 0 like the guitar string is because the wave function must be continuous everywhere. Does that make sense? Yeah. So that is what tells us that, therefore, the ends are fixed. So using what I just said, therefore the ends are fixed, and therefore now it becomes exactly like a guitar string problem. But instead of the well, we didn't really solve the differential equation, but instead of like F equals ma equals minus kx, right? That was normally how we solved the harmonic oscillator. It's this equation, which is very similar. This is like ma, right? Is kx kind of, right? It's very similar. It's solved the exact same way, so it is the same. It's just that, of course, now we call them different things now, like operators and stuff. Yeah. Okay. Does that make sense? So I'll do another one has all the same principles, but it's a little harder, and it's called tunneling. It's not actually a little harder. It's just that these 3 regions actually matter now. Before here, they didn't really matter because it's sort of obvious on the ends. But now we're going to do one where there's tunneling.
Is it because it tunneled through the 3 regions?
You'll see. I don't want to give it away. All right, so I'm going to erase like literally everything. Is that okay?
Yeah.
Okay.
Do it. But I don't even know how to use it. I don't know how to use the button. It's cute. I have like small cuts everywhere. I realized it until I put on pure all this morning.
So I'm going to erase
Yeah.
the Schrodinger equation.
Where is it? I'll bring some Swiss Miss.
Let me just find the. All right, these are not super thrilling. Okay, so this is going to be called. So I have to start off with one thing before I go to the tunneling. which is called a free particle. So remember we had, well, actually, I'm going to write something here, but I'll get to it in a second. We have there's sort of two possible solutions to this Schrodinger equation. Two possible types of wave functions. One are called stationary states, and one are called free particles. Now, stationary states, we literally just did one. The infinite square wall is a stationary state. It just means one way you could say it is that the expectation value of the momentum is 0. Okay, fine. That's a lot of work to show. But you could just say like it's trapped. I'll say that. Trapped. That's a better way to say it. So remember, we saw that clearly the wave function was trapped. It was completely inside one thing. Now, in that case, it was literally completely trapped. It was 0 everywhere. It doesn't have to literally be 0 everywhere. It could be something where it sort of decays to 0 on the ends. So essentially, there's one region where it is, and then it's not other places. Sounds a little silly, but that's kind of what a stationary state is. Now we're going to do what's called a free particle, which is sort of a slightly different, identical equation. Right? They're the same. That's why they're not. They're in the same unit. They're two types of solutions. Now, what if we have a free particle where, let's just say v equals 0 everywhere? That's kind of what it is. This is the same thing as this. Free particle means v equals 0 everywhere. What do we get? Well, let's just go right ahead. Let's not spend too much time thinking about it. We could just plug it in and see E psi, because v equals 0. And now what do we get? We kind of do the same thing we did before, where we have 2me over h bar squared minus psi. Okay, so now this looks the same as what we had before, but now we don't have any boundary conditions, right? So how do we solve this without any boundary conditions? Well, actually, sorry, do I have the sign wrong? No, okay, that's fine.
Where does the U go?
Sorry,
Like,
U?
Is the V the U?
Oh, yes, does he say U?
I think.
Okay, you could put U, that's fine. Well, let me look, make sure it's the same. Yes, U is the exact same thing. I was using V because most books use V, but
Okay.
it's the same. This means a potential. Yes, he wants to be a little different, so that'll be fine. Okay, so now I'm going to call this K, just because, why not? Just because I don't want to, you'll see, I don't want to write it in exponential. But what we get from this is, it's actually the same as what we had last time, but we can't use the sign, well, we could use the sine cosine, but we want to use the, because it's a free particle, we want to use the form that looks like this. Right? So remember, this is the same as the one we had before, but because if we just write sine cosine, we can't really see the left and right moving parts. So if they say it's moving to the left or the right, now we know that this is moving to the right and this is moving to the left. Do you remember this from the wave things? Yeah. Okay. Okay, and that's it, actually. That's the answer. That's literally the answer for a free particle. If they say, okay, that's it. That is it. Now, the reason that it's so general and there's so many constants and stuff is because they didn't really tell us enough information here. They didn't really tell us like what's happening or anything. So that's as close as we can get to an answer. However, so we know this is the solution. But if we have, let's say, not it's okay. Actually, well, okay, free particle. I'll write the solution again. Now, what if we have something like this? So this is x here, and this is 0. This is a. This axis here, of course, is the potential v, and this amount here is, I'll say u naught. U naught is an actual value. It's not. This is a function, but now I could write u, which remember is also v, as another, like a piecewise function. Again, I could say it's 0 at x is less than 0. It's u naught at 0 is less than x is less than a, or whatever, and then it's 0 again at x is greater than a. Okay, that would be another way to write it. So this, the name of this, if you want to give this situation right here a name, is called the finite square barrier. Now, if they tell you what is the actually, okay, we'll do this first. This might be getting to next week. Is this, do you have a problem like this with tunneling?
We have tunneling problems.
Okay, I think I just realized your tunneling problems are like this, right?
He did that in class.
Oh, okay. I should probably do this instead then, or both.
He drew that. That's all.
Okay. Well, I'll draw this so we don't forget. I want to do this too, because these look like things that could be trapped. This is not. This is a free particle, so nothing's trapped here. So I was going to say though, well, the thing you do with this problem is find the transmission coefficient. Which just means the amount of the particle that kind of gets through. That's sort of a way to say it, right? Like, yeah. So what we have is, so how we do this is just say, well, assuming now we have a free particle, let's just say it's going inward to the right like this. That means that we have a function that looks like that. Okay, we're using just by hand here. We're just setting it to be going this way, because if it was going the other way, it would be the same anyway. It would just be coming from here. So we have the free particle here, but then, so this is region 1, region 2, and region 3. And to describe the wave, so remember, the point of this was, the point of all quantum mechanics problems is to start with a potential and go to a wave function and energies, although, well, energy's not really going to matter here. It's not going to be, well, anyway, we'll see. So to find the wave function everywhere, we're going to need to find it in region 1, 2, and 3, right? That's just all of space. 1 means less than 0, 3 means greater than 8, right? And so we know that at region 1, it looks like this. The reason we know it's this is because this is just a free particle. We just say it's moving to the right, that's fine. That's it. So this is it. In region 2, though, what do we have? And let's say that the free particle has energy, as I should say here, has energy E, which is less than U naught. Okay? So what that means is if we plot how much energy it has, let's say it has this much energy here. That's less than U naught. So if we have some wave coming in like this, we're sort of in for some trouble, because it doesn't quite have enough energy to make it over to go over this thing. So what do you think is going to happen? Well, let's find out. So in region 2, we have the same Schrodinger equation. D squared psi dx squared equals, now what do we have on this side? E minus U of psi. Well, if we know that E is less than U, okay, now this number, the difference, so that's this number here, right? E minus U. we know that this is actually a negative number, right? So this number is actually negative, which means if we want to make it positive, we could say it's like minus u naught minus e. You might think this is really, why am I doing this? Is really weird, but trust me in a second. This is now a positive number here. I could actually, you know what? Let me change it. I'm going to write minus delta E, where delta E is the difference between it's u naught minus E, which is positive. Okay, does everyone follow so far? All I'm doing is just changing some notation to make it easier later. If you kept track of all the signs, it would be the same. You don't have to do this, but so this is minus delta E because it's the negative of the difference in energy. Now on this side, notice that we have a minus sign too, so they actually can cancel, and we get the same solution we had before, but now it's not going to be. There's not going to be an I anymore. There's no I in here, and the reason is because there is no minus sign. So like, I'm going to have to erase this again. So we had, so before we had like minus, before we took this and sent it to, let's see, minus 2me over h bar squared psi equals d squared psi dx squared. This is just like minus k psi equals d squared psi dx squared. This is what we had before. And remember that when we, what we're looking for is a function who, when we take two derivatives of it, gives us a negative number, right? If we take e to the I kx, two derivatives of this gives us I times I, which is minus k, which is this, okay? Now, because we have positive numbers on both sides, we have this, right? This is solved by that. Well, it's radical k, but whatever. Does everyone see that this is like a very key difference between this is actually literally the difference between something being transmitted and something tunneling. Okay, e to the I kx is a wave, right? E to the minus kx, like a real exponential, is like a decay, right? It doesn't oscillate anymore. And the reason is because in this differential equation right here, whether or not you have a minus sign here. If you have a minus sign here, solutions look like this, which is like sine, cosine, waves. If you don't have a minus sign here, solutions look like real exponentials. The reason, and I'm not, this is not a, trust me on this, this is not one of the things where you can trust me. You can literally just plug it in and see that if you have an I, you'll get a minus sign here. If you don't have an I, you will not get a minus sign here. And the fact that the energy of the particle is less than the energy it needs means that you'll get this real exponential solution. That's why I made this positive, so that we could see that it cancels the other negative thing, right? Therefore, we get this type of solution, and it's really A and B, and then when we plug in some boundary conditions, we'll see in a second that you're just going to get this term, the negative exponential. And what it's going to look like, so I'm going really fast just to show you the final solution, because once you see the final solution, it will make a lot more sense. You have a wave that looks like this with this much energy. Once it hits here, it's trying to go through somewhere where it has not enough energy to overcome it, so it will just decay exponentially like this. And now it'll have some lower amount of energy, right? But it'll still, over here, it's a free particle again, so it'll be like a wave. So this is called tunneling. Now, it also happens in the thing I erased, but it also happens for stationary states too. It's just when a particle doesn't have enough energy to get over a potential barrier, right? If it's infinite, then it's like a wall, it stops. There's no way. But if it's close, and here it's close, then going through it just costs it some energy. It has some decay like this. And the reason that you went from oscillating, so this is like wave, decay wave in these three regions, the reason that there's a decay, that this region's different, is because the Schrodinger equation, or any wave function that looks like this, whether there's a minus or plus sign here. Okay, does everyone see that? I'll say it. I'll stop for a minute and then I'll say it again, because it's very. This is like the key difference between the two types of solutions.
So there's no I, it's just like e to the...
Yes, there's no I. If there was an I there, you would take two derivatives and you'd have to get a minus sign type thing. So here, I'll just say it one more time in a little more, hopefully, like, way that agrees with what you just heard. This is the Schrodinger equation, and it's a wave equation, right? It looks like a second derivative equals something with a number. And there's two types of solutions. This number here is E minus, is the energy of the particle minus the potential it's going through. If this number is positive, that means that the particle is sort of above, has enough energy to overcome something. So it's like traveling in a wave above with whatever it's, flying over, right? If this number is negative, that means that the energy it has is less than the energy it takes to be in some material, right? In other words, you're flying a plane at a certain height, that's mgh, that's your potential energy, and this is a bad example, but there's a mountain that's in your way. In that case, it's classical, so you will not be able to get over the mountain, but if you are a wave, in a wave function, you would have this number be, so again, the E is less than U now, you don't have enough energy. This is a negative number, so therefore this negative number cancels this negative here, and you end up getting this type of equation with positives, there's no negatives anywhere. Solutions to this are real exponentials, which involve decays. They're not waves anymore. If it was the other way around, where you do have enough energy, you have a minus sign, there's a minus sign here, and the solutions to this look like e to the I things, which is, remember, the same as like sines. So those are waves. So in other words, the moral of the story is that if you have enough energy to overcome your potential that you're in, you'll be a wave. And if you don't, you will exponentially decay. And we'll see that the exponential decay, in other words, how much do you decay? Like, I just drew this here, and it's just from this function. But remember, this k is not just a new number, it's actually coming from these things. So you'll see that the k actually depends on the difference in energy. If you're like, have way less energy, like if the potential is huge, you'll decay much faster. And if you're very close to the top of the potential, you'll decay very slowly. Right, does that make sense? That's kind of intuitively that kind of...
Less energy will be lost.
Yes, exactly. So if you want to find the energy here and the energy here, and then compare them, that would be how much energy is transmitted. So I'm not going to... Sorry,
and the closer the energy is to the potential, the more energy it'll have at the end.
Yes, right. So if you imagine, so here I'll draw some pictures. If you had like this, so if it's the same width and you had the same energy, you'll get like a much steeper exponential decay, right? But if you had very close to the amount of energy, like you right under it, right, it might decay like slightly, and then you'll have this much at the end, kind of thing. Also, if it was really narrow, you can just imagine. I mean, it would look identical. If it was very narrow, you could just like cut it off here. If it was this shape, it would just be like that, right? The thing doesn't know how far it has to go. It just starts decaying, and then when it hits the end, it's like, oh, well, great, I can be a wave again. And all that is because of the change in sign of this term here. So this is either plus or minus, obviously. And the plus or minus determines whether we have an imaginary number in the exponential solution. And imaginary numbers mean we have waves, which means we have free particles, and real numbers means we have like decaying things usually. But yeah, okay. In this whole thing, this is not a stationary. None of this is a stationary state because the average momentum would not be 0 because we chose that it's moving to the right. Okay. All right. I can do a real tunneling problem. This is kind of a tunneling problem, but I didn't really solve for anything because I don't want. It'd be a lot more work. What you could do is literally just do this. Remember. So to solve. Okay. Let me just explain how you would solve this without actually doing it, because it's a lot of writing, but it's identical to everything we've done so far. There's nothing new here. All we need is that we know the energy and we know the wave function here on region 1. Region 2, we know the form of the solution, but we don't know, what we need now is the boundary conditions, and we know that the boundary conditions mean that the wave function has to be continuous everywhere. So therefore, at x equals 0, we must have whatever, that number here. So I don't know, however you plug that in. And then we get that it decays somewhat. The amount that it decays is given to us by k. K, remember, we're going to have to solve for, well, we don't even really have to solve for k. It just comes from, it's 2m radical e over h squared, h bar squared, right? Because that's this here. I just called it k. I should really call it k squared. Not put a radical here, just to make it consistent with all the string problems we've done last semester. And therefore, this is really the solution out of this. Anyway, so that's what k is, so we don't even need to solve for anything. And then to find what about region 3, well, once we know the function in region 2, again, it has to be continuous. So we know, therefore, that find this energy level, find the amount of energy it has at the end, or just find the value of the wave function here. And now it's a wave like this, but now it has this much energy, and that's it. Still looks like a standing wave, though. And k should be slightly different, right? Because remember, k was actually 2m e over h bar squared, this k, and so therefore the k over here is going to be different because e is going to be different here, right? It's going to be a little lower. So I don't know if maybe next week you might have to have a problem like this, and I could go over it better there. But anyway, but this is the idea. So now I'll do, okay, now, unless someone wants me to do something else, but I was going to do like 2 finite wells, and then the probability of tunneling from one to the other, because I think that's one of the questions. Is that true, one of the questions on homework, or no?
It's like
I don't remember.
the probability of an electron tunneling through a barrier to that of a proton, comparing them.
Oh, yes.
Well, that's the first one. And then like the second and third one are kind of just tunneling probability, but it's more like just messing with the equations.
Like if you increase the width by
Yeah.
x,
Oh.
what happens? Those kind of things.
I see. So we have, so I'll do this.
Oh yeah, consider the infinite quantum well. What's the energy difference between n and n plus 2 quantum levels?
Yes, so remember that the first thing I did with the energy, remember I wrote it's like n squared, pi squared, whatever. That's literally the solution. That's what I mean by like, that's the one problem. Whenever they say infinite well, somehow you can get the answer from just that. So I wrote down all the energies.
Just changing n.
Yeah, and just subtracting. So that gives you the energy of the nth level. So if you want to find the energy difference, you would just plug those. You don't have to do the problem again or anything. You could just plug in for n to the e function, right? E equals n, some function of n, plug into the different values of n.
Maybe we can do that.
Yeah, sure. Actually, well, look here, I can just, so it's like n squared, pi squared, h bar squared over, is this right? I believe this is right, 2ma squared. So like this. This is the answer. So again, this is not something you could figure
Yeah,
out.
2ma squared, you said.
Yeah. Yes. 2ma squared. Yeah. This is not something that you know that I'm going to be like, well, clearly, then now we can look back on it's obvious. This is not obvious. This is very difficult to find, but this is it. It comes from the Schrodinger equation, obviously, and the states of the boundary conditions of the square well. And so, if we want to find the energy of the n+1 level, let's say we want to find the energy difference between, let's say they said energy difference between first excited state minus ground state. Right? That would be they give us two exact specific states. I don't think they didn't do that there, right? They just
You said n and n.
okay. So that's done. But if they said specifically at first, like, ground state is the lowest n you could have, and as we said, it's 1, right? It's not 0 because of all the things we talked about. So the ground state energy is pi squared h bar squared over 2ma squared. What's the first excited state? That just means the next, like the first one above the ground state. That would just be n equals 2, of course. So we get 4 pi squared h bar squared over 2ma squared. So what do we get here? What's the difference between these? Well, it's just going to be 3 pi squared h bar squared over 2ma squared. So this would be the difference between the energies of the first excited and the ground state of specifically of the infinite square well, or the infinite quantum well, whatever they call it. This is not true for like the energy levels of an atom, for example. That's a completely different thing. Now, if they said n+2 state, well, what's the n+2 state? Well, it'd be energy would just be n+2 here squared. 2ma squared. And then we get what? Well, we get n squared. Well, so the first term we get is going to be, if we just expand it, let me just write this, plus 4n plus 4, right? That's this number here. So if we, obviously we're going to get 3 terms. Now the first term is going to be n squared pi squared, blah, blah, blah. So that's actually going to be en, right? Because en is this. So the first term is going to be en, right? The second term is going to be 4, and there's just going to be an n here. So this is not going to be anything like this, but it's going to be 4n pi squared h bar squared over 2n a squared. And the last term is going to be 4 with no n. This is going to be like a constant. That's what we get. This is the E of the n+2 state. Now, of course, if we want the difference between the n+2 state and the n state, we just subtract these and we get just this quantity here. And we can see that there's a constant, which is kind of weird, and then there's a thing that depends on n, which is also kind of weird. So, in summary, that's a very weird question because you don't get a cool answer.
Where does the width come in?
The width is A.
Oh, so that's the same thing as like what it's saying L.
Oh,
So
yes.
just
They probably use,
change
if they put an
L.
L squared in the bottom, that's L. Yeah, that means that you have infinite, and it's 0 to L or whatever the width.
Okay.
I mean, you could also do, minus L over 2 to L over 2 if you want. That it would just be a little different. You'd get cosines instead because it would be sort of symmetric around. Anyway, who cares? It would be identical. Actually, that could be a good practice. Not that you really want to do more practice, but if you wanted to practice, you could literally do exactly the whole thing I just did with the infinite square well, but instead make it from minus L over 2 to L over 2, and you'll get different wave functions, you'll get cosines. But if you compute the energies, which you can do by just plugging your wave functions back into the Schrodinger equation, you should get exactly the same energies like this, because of course it's the same states, it's just labeled by something else. And that just shows you, again, that cosines and sines are the same functions, they're just labeled sort of slightly differently. If we have a barrier that it can't cross, that it doesn't have enough energy for, E, then we said, this is just the same thing I was drawing before, we could solve it in the 3 regions, and we would just have a decay, an exponential decay like this, right? And we know that the exponential decay would look like e to the minus kx. I don't want to write the whole thing again, but it would look like e to the minus kx. We know it wouldn't be positive because it wouldn't gain energy, of course. So basically, this is something like the wave function. There's a number here. in this region, and if you double the length of this region, then it's asked what the probability was or something.
To the energy levels if the width is reduced by a factor of 2. Is this the part?
No, that's for the well, I think. That you could do from.
Oh, the problem I asked about?
Yeah. Sorry. There's.
Consider an infinite quantum well with L. What's the energy difference between n and n plus 2 quantum levels?
Oh no.
That's what he just
Sorry. I meant. Sorry. No, I'm confusing myself. I meant there was one you asked about tunneling.
Oh.
Is there any on the homework that say the word tunneling?
Yeah, by how much, or compare the probability of an electron tunneling through a barrier to that of a proton.
It also says by how much does tunneling probability increase or decrease if we double the width and then
Of the barrier.
double the difference between the strength of the barrier and the energy of the particle.
Yes. Yeah, so those are going to all come from this equation. So the reason they come from this equation is this is what I was looking for. So when we use the Schrodinger equation like this, so I'll write it again a little bit. So remember what I was saying is if we have a situation where we don't have enough energy, this is negative and therefore the negative cancels here and we get a solution that looks like this. Now assuming that the particle has more energy on the left, we're going to get something that looks like this because it's going to decay. Okay? Now K, I just made up K, but K is really, if you actually solve this, and if I call this, well, I'll leave it how it is. We're going to e to the minus. All right, I'm going to confuse myself. This is just a 2m e minus u naught. Now it's u naught because, over h bar squared. It's positive now. So I believe it's going to be the square root of this thing. The reason it's a square root, remember, is because it's like k squared goes there. Yeah, it's probably written somewhere.
Tunneling probability.
Oh, yes. Oh,
I think
okay.
that's
I guess they want you to just use that.
She said I couldn't hear it.
Right. I see. So they. Okay, so this is literally section 9.2. Okay, so they do this exactly what I did. Figure 9.4 is the three regions I just drew. They actually have the actual wave function of the. It's just e to the ikx. So that's in region 1. So this is basically what I was just drawing and. Okay, this is kind of what I just did, I guess. But let's try to answer the actual questions. Yeah, and then so equation 9.26 and then wait, that's not right. A equals B. I don't think this is oh, sorry. Yeah.
And that's where you just use K for.
Yes, yeah. So K, okay, sorry. Let me do it a little more. So I kind of half did it a second ago. This is in region 1, psi 1 is this. But remember, if it has energy E, I just made up K. It's just a thing I made up to make the things easier. K is really, it's like,
Square root of
it's, yeah.
2me over h.
2me over h bar squared, all the square root if you want. Yeah. X times A psi 1 equals. Okay, so we're really going to do this now. So this is in region 1. This I got just by the Schrodinger equation. It looks weird. This number up here is just the, I'm writing both, even though if, in my opinion, we would never use K for any of these because it just makes everything confusing because K is just a new letter. In the book, they use K and they just say it, and it's of course equal to this. That's fine. Well, let's just write both. And now in region 2, we show that we get this. Now, really, we get this plus e to the plus kx, but by the boundary condition, remember the boundary condition said that psi of 1 at, so this is x equals 0, this is x equals a. So the boundary condition 1 says that psi of 1 at 0 has to equal psi of 2 at 0. And, well, so therefore if you plug in 0 here, we get, we get a, right, from psi 1. And therefore this equals, I should have written b because it's a new equation, right? And therefore this at 0, well, if we plug in 0, we get b. Well, okay, that makes everything easier. So this is indeed the same a as that. Right, does that make sense? Okay, so let me back up, right, because this is not sort of self-contained. So all we did so far is we have we didn't care about region 3 yet, but all we do is we care about 2 regions. In one case, we had a free particle, and so we just solved the Schrodinger equation. It just ends up being, I erased that. It ends up being a free particle because it has to have an I because we have that minus sign, because the energy is higher than the potential, which is 0. So we ended up having the Schrodinger equation with no U. This is the solution. We also have the plus thing that goes the other way, but we're just saying because we care about the transmission, we're just going to consider one wave going in, so that's fine. We can't solve for A. We can't normalize it because it's like a free particle traveling. So, I mean, we could if we were really did some careful parameterizations, but we don't have to do that because all we care about is leaving the ratio of what comes out of here versus what went in over here. That's the transmission. So it doesn't really matter exactly the values. We just care about the relative values. So we can leave it as A. Then I solved the Schrodinger equation in region 2, where we had exactly the problem, exactly the situation I was describing before, where this quantity is now negative because we're now in a region where it doesn't have enough energy to overcome the barrier. So this is negative, and therefore we get that this negative cancels, and we get a situation where we have a real exponential. The solution to that point is a real exponential. We have a k again, which is a little annoying because it's not the same k prime. K prime is up here. So then we get, this is our solution, sorry, b. We really, of course, get b e to the minus k prime x plus c or whatever, e to the plus k prime x, but the plus would be a positive exponential, and we know, of course, that that doesn't make sense because it wouldn't get higher energy, so we can throw that away. So we get this, and now all we did now is solve 2 Schrodinger equations in 2 situations with different signs for this term. That's the only difference between everything we've written so far. And all we did here is just apply the one boundary condition that we know is true, which is that the wave functions must be continuous. We didn't even use the derivative because, again, we can't use the derivative being continuous because there's an infinite jump here, right? Infinite jump, by the way, doesn't mean it goes to infinity. It just means it jumps infinitely fast. It's not like a smooth wave function or potential. And from this, we get A equals B, right? Therefore, we get this. We can just write, we'll call it A still, right? So therefore, psi 2 is this. Now remember, the whole point of this is to find the wave function everywhere. We have psi 1. I'll use red because we have psi 1 here, and we have psi 2 right here. Sorry. there should be a little, there should be a minus sign here. All right, I really should write u not minus.
U minus E.
Yeah, sorry. Remember, under the radical, it has to be a real number. Sorry, it has to be a positive number because the whole thing was real. And that only happened, it only canceled this if I switched these to make it negative, right? So just, this thing. You could also put write a minus sign and leave it. That would look a little weird to write a minus sign under a thing, but anyway, whatever. So that's it. So we have two parts done so far. We have the wave function here, we have the wave function here. Now all we need is the wave function in region 3. And it's literally the same exact Schrodinger equation as in 1. It's a free particle. So in region 3, we get this, right? It's the same exact thing as in 1. Of course, now I'll call it E3 because it's not the same energy necessarily, right? But we have some E3 and that's it. And then when we just get the solution again is exactly like this. So psi 3 is e to the I. It's still going to the right, so that's fine. Radical 2m E3 over h bar squared all under the square root times x. Now I'll write c in front because it's another constant. We don't know what the constant is. It's not going to be just the same as all the other ones because why would it be? We don't know yet, right? But we have to apply, now right here, we're applying this boundary condition. So again, there's 2 points where we change functions, so we have to apply the 2 boundary conditions. This one is now psi 2 at A has to equal psi 3 at A, right? I'll just erase this actually. Right? Now what's psi 2 at A? Well, that's actually not obvious. It's something kind of complicated. Psi 2 at A is A, big A, e to the minus radical 2m u naught minus e over h bar squared times A, right? Okay. It looks really weird, but this is just a number, right? This is e to the minus, and all of these are just numbers, right? This is literally just a single number. So it looks weird, but that's fine. It's not a function. And on here we have psi 3. Now remember, we know what psi 3 looks like. It's this, c e to the I 2m e3 bar squared at A. Okay. And now the whole point of this was to find C, right? And so C, therefore, this is also just a number, right? None of the, again, there's no, when I say it's a number, I just mean that there's no x's in it. X is a variable. Here they're all numbers. They're not variables. So C, therefore, is, well, it's going to be kind of complicated. It's going to be A times this divided by this, right? Like, I'm just putting this all underneath. So it's A times e to the minus, blah, blah, blah. Yep. Okay, and now a bunch of stuff's going to cancel. Can I just look at the... Okay, so okay, so this is equation 9.27b, and because they've defined a bunch of, okay, what did they set A to be? Yeah, so because they've chosen some very nice, like, just variables to mean these giant things that I've written, and perhaps they've not told me what they meant. I don't know. Hmm. Oh, no, they. Okay, yeah, so alpha in the book, alpha is, in the book, this number here is, they call it alpha, and they call something else, they call it A, D, I don't know, whatever. Yeah. Actually, I should have just looked at the book and used the same conventions. Whatever. And then 3. Yeah. Okay, whatever. And then hopefully we can cancel some things out and find C. And then we'll have psi 3, which is this. And then, now, they do tell you the answer in the book, so you should look in the book for this. It looks kind of like this with something in it. But basically, then you'll get the tunneling probability is going to be just psi 3, the probability of finding something at, it's going to be psi 3 squared over psi 1 squared. And the reason, of course, is because psi 3 squared just means finding the thing over here, right? And psi 1 means finding it over here. So if you said what's the ratio of the probability of finding it on the right side versus the left side, it'll give you some proportion here. And it'll, of course, the wave functions mostly are going to cancel out, and you'll get something that it's probably going to be like c squared over a squared or something like that. So it's probably going to be something like this. Anyway, it's going to be whatever they just told me to write the answer. It's going to be e to the Oh, well, sorry. We should plug in at A and we plug in at 0. It's really the wave function plugged in at A and the wave function plugged in at 0. Because we have to actually plug in values, otherwise we'll get x's in here. We can't have x's in anywhere, right? And this is going to be just, now apparently, hopefully I didn't make any mistakes. Times A, and that's it. Okay. Oh.
That was not a good O.
Sorry. Okay, sorry. I made a small mistake, and I will. Let me first mention that figure 9.5 is literally this figure right here. So if you want to see a picture of it drawn by a computer, then figure 9.5 is literally identically to what I was trying to draw here. I made a small mistake, which is that I said that there was another energy E3. That's not true. It's the same energy because it solves over in this region. The Schrodinger equation is identical to this. So the solution is literally exactly identical. So there is no E3. It's the same as E. That's why. So everywhere I wrote E3 should just be E. Hopefully then it solves every, yeah. Yeah, I don't know why I was thinking, yeah. The wave function, the reason the wave function has a lower magnitude here. It should have a lower magnitude. If it didn't have a lower magnitude, then the tunneling probability would be 1. Right? But it better have a lower magnitude, but it doesn't necessarily have a lower energy. It actually doesn't have a lower energy because the Schrodinger equation on the third region is exactly the same. Okay, and you get this? Everyone okay?
It's Joe's stomach.
It's that time. Yeah, and so now you can answer questions like A is the, in the book they use D, but A is the length of the, it's this length here, right?
The width of
The width, sorry, the width, yes, of the barrier. So if you double this, what will happen to the probability? You can figure that out. And if you change the mass m, this is where m is the mass of the particle that you're considering, you could see what happens there too.
It's like a proton versus an electron.
Exactly. So they tell you the ratio of them or whatever. Just
Yeah,
basically,
plugging it in.
yeah, just plug in the p of tunneling for one m and then plug in for the other m. Of course, you can't. Well, anyway, you'll see.
It was so hard to put in the calculator.
Yes, I.
Got 0, and it's not the answer.
Oh, well, if you put it in a regular calculator, it'll probably be so small that it will say it's 0, because it'll be like 10 to the minus 50 or something. Not really 50. 10 to the minus
Something small.
30. Because h bar squared, well, it's in the denominator. Anyway, whatever. H bar squared is very small. But the m is very small, and the energies are very small. The width is very small. One of the questions in the book that you don't have to do was like, calculate the probability of a person tunneling through a wall.
wanted to ask him.
What
What were they even asking by that?
What were they? They wanted you to assume that you are described by a wave function, which you are. You can be. I mean, you can be. It's just kind of not something you normally do. And you would plug in your mass here, m,
Oh,
and you would plug in the thing. You would get that because your mass is so big compared to
don't know that.
h bar and compared to all the other things that if you plotted this, it would look like if you're a free particle, and then you have a wall that has like energy like this, you would get that the your wave function into the wall would go like, it would go down so fast, and that's literally that's how we describe. That's the explanation for why things. It's not like, oh, people aren't wave functions. That's not true. They are. We are. I'm saying it like I'm not. Person. We are. You can just. I mean, you could. Again, this is. It doesn't really matter. Now I'm getting into like a philosophical thing, but it's not about whether it's really true. It's just this describes things correctly. Okay, that's the point. So does it describe humans correctly? It does, in fact, describe why we can't go through walls. And actually, in fact, it describes that we could if it was a small enough barrier, I suppose. I don't really know what that would mean, but every object can be, if an electron can be described by, yeah. If an electron can be described by a wave function and a proton can be described. Now, a proton is actually made of quarks, right? It's made of 3 quark. So a proton is made of other things, and yet it can still be described by a wave function. So you might think, oh, well, people are made of all these different things, so we're not. But no, everything has a wave function no matter what it's made of. It's just has much more mass, and so tunneling happens a lot more rarely, and that's it, I guess. Also, we have a lot more energy in all of our particles than an electron has. So again, those things together make the e to the minus some huge number. And e to the minus this is only like a reasonable number when these m's and e's and stuff are close to h bar, and h bar is extremely small. So when m and e are very, very small, when it's like electrons and stuff, and when the energy barriers are very small, when it's close to h bar, remember h bar is like minus 10 to the minus 34, right? Electron volts or whatever, or joules, I think. So when it's like that huge, I mean, we have hundreds of joules or thousands of joules or something. That's way, 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 way too high to overcome this h bar, and so we don't tunnel through anything generally. I mean, we do, but not very much.
Add to the wall.
Yes, exactly.
A proton is larger than an electron, right?
Yes,
So
a lot
the
larger. Yeah.
probability should be smaller.
Exactly. It should be. You should test it. But indeed, yes, it should. The probability of the proton should be smaller. And that's how I was saying to you probably that's how fusion works, like in the sun.
Yeah.
Like in the nuclear fusion works by neutrons, or any nuclear process works by there's a nucleus, and there's other particles like protons and stuff that are outside the nucleus, and they're somehow get into the nucleus. And you might think, well, how do they get in? Like, isn't there some kind of isn't it like they repel because they're both positively charged? And they do, and you might think, oh, maybe they just need to go fast enough, and that's sometimes true. But really, it's actually mostly the case that they actually tunnel from outside of the region. So it's not a barrier. It's not an infinite barrier, but there is a potential barrier that looks like if here's the nucleus, there's a potential barrier that looks kind of like this, because this is like it's repelling charge. So if positively charged things try to go here, they tend to be pushed away. Like that's what the potential is telling you, is that they want to slide really far away. That's like I shouldn't even, well, okay, and then the reason I'm drawing that it goes down here is because there is very, very small, close range nuclear forces that pull things together. I mean, that's how they stay together. So if you get close enough, you can stick in. So what happens is that particles with this much energy actually tunnel into the nucleus, and that's how like the light from the sun occurs, is from this. I mean, because this reaction then emits a bunch of photons and stuff. So that's literally how most of the sun works, and nuclear reactions and nuclear decay. That's how nuclear decay, I should specify, this is exactly 100% how nuclear decay works. Because in nuclear decay, there is not a bombardment of energy like in the sun, where you could be like, oh, it's just going so fast that they just ram into each other. In nuclear decay, it's just sitting there, right? So how do the protons and neutrons get out of the nucleus? Aren't they bonded together? They are, but they tunnel exactly the other way. They eventually randomly get enough energy to tunnel outside, and now they're repelled by electric charges. So if you're asking about what in real life, this is in real life how real things happen. This isn't like isn't it funny that if we use these quantum mechanics things and we call things waves, we can like get silly little things and, oh, okay, electrons do this. If you put an electron in a box, but like you're never gonna put an electron in a box. So like doesn't mean anything. Like, you know. But this is literally how real processes, like if you didn't know about this and you thought a lot about and worked a lot in nuclear reactions, you would literally conclude that they're impossible, because they actually are impossible without this. I mean, if they're described by particles, like particles with forces on them and stuff, it would be impossible. There is not enough energy in a nucleus to escape, to shoot out an alpha particle or a gamma ray or whatever. There's not enough energy. But there is enough energy to tunnel, to go through this barrier, and that's literally what happens. Anyway, whatever. I've been rambling. But yeah, anyway, so that's a real life example. Chernobyl, exactly, yes.
That's a great show.
It is a great show. Did they win a thing? Did they win
Yeah, they won a few things.
an Emmy?
Like one of the